Molecularity of a reaction. See, there is one more property of a reaction which is called molecularity of the reaction, which is basically used to understand the mechanism of the reaction. I'm repeating again, it's a property of a reaction, this molecularity, and it is basically used to understand the mechanism of the reaction. Now you need to understand that the reactions basically are of two types. They can be elementary reactions or they can be complex reactions. Elementary reactions are those reactions which takes place in single step. And normally whatever the reactants we find involved in these such reactions, they collide simultaneously to form the product. Such reactions are called elementary reactions. Now what are complex reactions? The reactions which takes place in several steps are called complex reactions. Now what is molecularity of the reaction is? It is basically used for elementary reactions. Now molecularity of a reaction is defined as in the elementary reactions, the number of reactant molecules, the reactant species, whether they are atoms or ions or molecules, reacting together, colliding together simultaneously to form the product is called the molecularity of the reaction. I'm repeating again, let us understand this. In elementary reactions, the number of atoms or ions or molecules colliding simultaneously to form the product is called the molecularity of the reaction. So this term is mainly meant for elementary reactions which takes place in single step. And if we have only one reactant involved in the reaction and it directly changes to the product, the reaction is called unimolecular reaction. Unimolecular reaction, like we can have the example of the decomposition of ammonium nitrite, which on decomposition forms nitrogen and water. Remember, as per the order of the reaction, we will say that these are the reactions whose order is 1. So whenever or all those reactions in which the order is 1, we can say that they are unimolecular reactions. Now there can be two reactants present in the reaction which is converting into or reacting together to form the product, and we can have the example like, or there can be reactions in which two molecules of the reactants are reacting with each other to form the product, like we can have two molecules of HI reacting or colliding with each other to form hydrogen and iodine. Such reactions are called bimolecular reactions, or we will say that these are the reactions in which the order is 2. So similarly, we can have 3 reactant molecules colliding simultaneously to form the product, or there are 2 different reactants, but their 3 molecules are the one which are colliding together to form the product. They will be called trimolecular reactions, and we say that their order is 3. But remember, we won't find the order reactions with order 3 or more than 3 very common. They are very rare, or the reactions with molecularity 3 or higher than 3 very rare. The reason is because the probability of the collision of the reactant molecules with one another becomes very, very less. So such reactions are very rare or very slow, or are usually not seen around. Now let us move to some other examples. We can have many other examples, like we normally take normal organic reactions, which appears to be simple but are very complex, which takes place in series of different steps. Each step is taken as the elementary reaction. Now we need to find out what exactly is the molecularity of such reactions. See, our purpose of giving molecularity is to find out what exactly is the order of the reaction is. Basic idea is to give a theoretical explanation of the differences which we are getting, that why not stoichiometric coefficients are the order of the reaction, because whole of the reactants are not reacting simultaneously, or the reaction is taking place quite slowly in different steps. So in elementary reactions it becomes very easy. For complex reactions, the molecularity concept says, to understand the molecularity, let us go into the mechanism of the reaction, or how the stepwise reaction takes place. Now molecularity says, in the different steps in which the reaction takes place, find out the slowest step, the step which is taking the maximum time to get completed. That will be called the slowest step. And from that slowest step, which is also called the rate determining step, the number of the reactants or the reactants involved in this will be called the order or the molecularity of the reaction. Let us see with certain examples, the examples of the complex reaction, that how the molecularity helps us to understand the basically order of the reaction, or how it takes us into the mechanism of the reaction. Let us take the example of a complex reaction in which N2O5 decomposes to give you NO2 and O2. We know order experimentally comes out to be 1. Rate expression as per the rate law is like this. Now, when we goes into the mechanism of the reaction, we find that it takes place in 2 steps. It's a complex reaction because it is very clear. If it is not a complex reaction, then it's an elementary reaction. Then it's the number of reactant molecules reacting in this, the elementary reaction would have been equal to the order or molecularity of the reaction, which is not taking place in this. So it is very clear it's not an elementary reaction. It's a complex reaction which when actually was studied in detail, what we find is that it takes place in 2 steps. Like first, this NO2 N2O5 molecule dissociates to give you one NO2 and one NO3, nitrogen dioxide and nitrogen trioxide. This is an intermediate, a very unstable species, which as soon as it is formed, directly reacts with one more molecules of N2O5 to form what? 3 molecules of NO2 and 1 O2. When these are combined, this gets cancelled, so we can have overall reaction as N2O5 forming 4 NO2 in total and 1 oxygen. So you can see that the overall reaction comes out to be the same as the original one, and these are the 2 steps in which this reaction takes place. Now out of these 2 steps, you can clearly make out this one is the slowest step. Remember how we can make out which step will be the slowest step. The step in which the intermediates are formed is called the slowest step. And this will be the step in which the maximum energy will be consumed in this, and this intermediate is formed. The reaction in which the intermediates reacts are always the fast reactions because their energies are very high, so it will be the fast reaction. Now in the slowest step, how many reactants are involved? How many reactant molecules are involved? It's only the 1. That is why we say that this reaction is having molecularity 1. It's a unimolecular reaction, or the order of the reaction is 1. So what we find is that the mechanism proposed, mechanism given or mechanism determined is supporting the order which is obtained experimentally, and this is what is the benefit of the molecularity of the reaction, is that this property leads us to the mechanism of the complex reactions, which actually supports, or which is the theoretical explanation of the experimental order which we get also. Let us take some other examples. Let us take another example of the decomposition of hydrogen peroxide into water and oxygen in presence of iodide ion in alkaline or basic medium. See, in this what we find is the hydrogen peroxide decomposes to give oxygen and it forms water. Now, as per this reaction, it appears if this cannot be an elementary reaction. If it would have been an elementary reaction, then the order of this reaction or molecularity of this reaction would have been 2. What we find is that the order is found to be 2 experimentally also. Yes, it is found in experimentally also to be 2, but what we find is that the rate expression says it is K, H2O2 and I minus. See, I minus in this was the catalyst which should not be involved in the reaction, but the rate says that this reaction is not actually proportional to the hydrogen peroxide concentration to the power 2. So it's not the square of the concentration of hydrogen peroxide, and that is why its order is 2. It's basically depending upon what the concentration of the H2O2 as well as on the concentration of I minus. And this is how the 1 plus 1 is making its order to be 2. Now this is justified by the mechanism of the reaction, which takes place in two steps, in which what we find is hydrogen peroxide, iodide ion combines with the hydrogen peroxide, and what it forms is it reduces this into hydrogen water, and itself gets oxidized to IO minus. hypoiodide ion. Now, as soon as this hypoiodide oxidizing agent is formed, it again combines with one more molecule of hydrogen peroxide, and it forms again then one water, gets reduced to I minus, and now it is basically oxidizing it into oxygen. Now, when we balance this equation, what we find is this IO minus, which is an intermediate, gets cancelled. The I minus gets cancelled because whatever the catalyst what was consumed, it was formed again here. So what we find at the end is this is H2O2 plus twice of H2O2, which is on decomposition is forming what? Twice of water and oxygen. So what we find is this step being the slow step, because in this the intermediate is formed, this being the fast one, and since in the slowest step both the hydrogen peroxide and the iodide ions were involved in this, and one molecules of these were reacting together to form the product, what we say that it's a bimolecular reaction, and the rate expression supports this. The mechanism support the experimental order, and this is how we justifies the mechanisms and the order of the reaction by the property called molecularity of the reaction.